To answer part A, we first notice that the initial total momentum is 0. We have 4 times 3, or 12 kg per second for the 4 kg ball, and we have negative 12, 2 times negative 6 for the 2 kg ball. So as one system, these two balls have a total momentum of 0 momentum. From the principle of conservation of momentum, we know that the total momentum of these two balls must remain as 0 throughout the collision. So if one of the ball comes to rest at one instant, then the other ball must also be at rest. If not, their momentum will not add up to 0, and that will violate the principle of conservation of momentum. Let's now move on to part B. To solve part B, we first form an equation out of the principle of conservation of momentum. So the total momentum before the collision, which is 4 times 3 plus 2 times negative 6, should be equals to the total momentum after the collision, which is 4 times negative v1 plus 2 times v2. So we get the first equation here. With two unknowns in one equation, we can't solve anything, so we need to bring in another equation, which is going to come from the fact that the collision is an elastic collision. We know that for an elastic collision, the relative speed of approach is equals to the relative speed of separation. The speed at which the 4 kg ball was approaching the 2 kg ball is 3 minus negative 6. And the speed at which the 2 kg ball was pulling away from the 4 kg ball can be written as v2 minus negative v1. And so here we get our second equation, and the rest is mathematics. So after solving the simultaneous equation, we obtain v2 is equals to 6 meters per second. Let's move on to part C. So this is the velocity time graph. The blue line is for the 4 kg ball and the green line is for the 2 kg ball. For the 4 kg ball, its velocity went from 3 meters per second before the collision to negative 3 meters per second after the collision, from positive 3 to negative 3. For the 2 kg ball, it went from negative 6 to positive 6. Actually, one can tell quite easily that the steeper line here belongs to the lighter ball. This is because during the collision, the two balls experience the same force. So the lighter ball will experience a larger acceleration, which shows up as a steeper line in the velocity time graph. This is the momentum time graph. Again, the blue line is for the 4 kg ball and the green line is for the 2 kg ball. For this graph, notice that during the collision, the two lines have the same steepness. This makes sense because during the collision, they experience the same force. Remember, force can be equated to the rate of change of momentum. So experiencing the same force means that the two balls will experience the same rate of change of momentum. This also illustrates very clearly why the total momentum of the two balls remain as constant, because during the collision, the rate at which the blue line is dropping is matched by the rate at which the green line is rising. So the summation of the two momentum remains constant. And the last graph here is the kinetic energy time graph. The Ke of the 4 kg ball was 18 joules before and after the collision, and for the 2 kg ball it was 36 joules before and after collision. This can be calculated quite easily using the formula half mv square. This is an elastic collision. That's why the total kinetic energy before and after the collision remains the same. Do notice that the kinetic energy during the collision is not constant. I hope that makes it clear to everyone that when we say that a collision is elastic and that kinetic energy is conserved, what we mean is the kinetic energy before and after the collision is conserved. But during the collision, when the two balls are still interacting with each other, the kinetic energy is not conserved. In fact, the kinetic energy must be stored somewhere as potential energy, either as some kind of elastic potential energy or in the deformation of the balls. But for an elastic collision, what it means is this energy which is stored in the potential energy will eventually be returned as kinetic energy of the two balls after the collision. So get it? The total momentum is conserved throughout the collision, before, during, and after. But for the kinetic energy, for an elastic collision, the kinetic energy is only conserved before and after, not during the collision. Let's move on to part D. A completely inelastic collision is very easy to solve because after the collision, we know that the two balls will move off, will be traveling at a common speed. So we just need to form an equation of the principle of conservation of momentum. The total momentum before the collision, which is 4 times 3 plus 2 times negative 6, should be equals to the total momentum after the collision, which can be written as 6 times v. And for that, we can solve v to be 0 meter per second. Okay, I hope you found it useful, and thank you for using XM Physics.